So I guess everybody. Okay. Okay, well, thank you, Dana, for letting us know everybody can hear us. And we were just getting ourselves organized. So welcome, everybody, to our webinar on thermal energy and networks. We have a great lineup today. So I just want to give everyone, though, one more minute for people to sign on because it's just 9 o'clock. So if everyone could just hold tight for about a minute or two, we'll just make sure that we get more people signed on because I see the participant number is growing. And then I'll introduce who our panelists are today, and then we'll hear from them. So thanks, everybody. Just give us sort of 2 minutes and we will get started.
All right. Just so you know, I'm Jacob Knowles from VR+A. So Tom Martin from VR+A is going to be supporting Dennis Karlberg on the
Okay.
BU presentation. Since I have a conflict, I think at the exact time that Dennis and Tom will be presenting, I think I should probably jump back into the audience
Okay.
invite, but just want to say hi. Thank you for
Oh,
having us.
sure. And as everybody who's listening in on the webinar is going to just listen to some of our organizing, just for those that are panelists, you can keep your camera on the whole time. You can turn them off and put your camera on when it's your turn. You'll be sharing your own slides. So when you're done with your presentation slides, if you could take them down so that the next person can share, that would be great. All right, so it is 9:02. We're going to get started. So again, welcome everybody to our, I think this is our fifth in our webinar series. So this webinar series is being hosted by Office of Energy Transformation, our Decarbonizing the Peak Focus Area Work Group, although this invite has gone out very widely. This session is covering thermal energy, and we're going to hear from the following speakers. Zainab Meghavi from HEAT. I think we have Jeannie on, so Jeannie Morris from Vicinity Energy. Dennis Carlsberg from Boston University, and Nikki Bruno from Eversource. And we're going to go in that order. So just to let folks know how this goes. So each presenter is going to give an overview, touch on a different topic, different aspect of thermal energy, thermal networks, thermal systems. Then we will have opportunity for some Q&A for that presenter after they're done. So for each one, we're allotting about 30 minutes total. So you'll hear from them. Then there can be some Q&A. If folks could please put the Q&A in the Q&A box, you'll write your questions in and we'll ask them. So that's how this works. So yeah, I've already see a question in the Q&A box. Will someone provide a working definition of thermal energy? Yes, I know our presenters will do that, so we will be touching on all that throughout this. And then the presentations and the recording of this will be made available on the Office of Energy Transformation website. So just for everyone, this is being recorded, and the presentations and recordings will be available. So with that, I'm going to turn it over to Zainab.
As long as I start by unmuting. It is lovely to be here, and I'm going to quickly share my slides. Let's see. All right. So I'm going to try to be brief and not say everything I want to say about thermal energy and thermal networks, but focus on two topics: the thermal energy opportunity, to make sure we're all talking about the same thing, and then the electric grid impacts potential of that. And you'll hear more about other pieces later. So HEAT is, by the way, a nonprofit focused on the thermal transition and meeting the needs of the future through innovation and transformative change. So I want to just start really quickly by clarifying that we are not, I am not speaking to any of the geothermal energy opportunity pictured on the left. It is not yet, by current technology, accessible for Massachusetts. So I am speaking only to the thermal energy opportunity that I call ambient. Some people have called it shallow. I think that's a little not the best name. So ambient, meaning the near surface, 1,000 feet down. The average temperature in Massachusetts is about 55. that is a giant thermal energy reservoir. So I want to start talking about that. It's often called geothermal energy. All of the pictures here are geothermal technologies. So I'm going to talk about geothermal ambient energy, and it is an anywhere, everywhere energy resource. It is stable and non-intermittent. And one sec, there we go. And why would I focus on the ambient? It doesn't seem like it's big, and I just want to make really clear exactly how big it is. So if you stop and think about climate change as a thermal energy regulation problem, and look at the actual numbers calculated, every year the Earth is absorbing over 10 times the energy that all humanity uses. The technical potential, as the IEA published last year in its first ever geothermal report, of geothermal is more than enough to meet all heat demand in many continents. There was a dearth of data. It probably meets it almost everywhere. So I think the importance and scale is easy to ignore because it is the normal around us. It is the environment within which we live and breathe. To try to highlight what this ambient geothermal, and particularly the geothermal energy that is in excess thanks to us humans, I've coined the term anthrothermal. Here is our Boston Harbor. Using NOAA data, calculated the change in thermal energy in the Boston Harbor is 3.4 degrees Celsius within the past 100 years. And that is, with the turnover rate, possibly equivalent to 1.2 million homes of thermal energy, to give you a sense of the scale that is all around us. So this thermal energy opportunity is massive, and we've been kind of fundamentally ignoring it. It is kind of part of our assumption of the world around us. It's small and incremental, a little like that frog in a pot. And so highlighting it and thinking about how we can use it in our energy system to meet the challenges is really critical. Last bit of thermal energy opportunity is that we also have an entire energy system that wastes a lot of energy along the way. This is a Sankey diagram from the US energy system. I should probably update it, but it's not that dissimilar today. And it basically shows that the energy we use at the other end of production is less than the energy we kind of reject or lose. And that lost or waste energy is actually primarily thermal. And so there is this opportunity all around the built environment for waste thermal as well, including, for example, sewer thermal, industrial thermal, and gosh, that hot topic, data centers. All right, so that's that thermal energy. Now for a moment to the technology. Let's clarify the technologies available to us here. We're starting with the geothermal heat pump. Yes, the federal government's now calling it geothermal heating and cooling equipment. But it's a little shorter to say geothermal heat pump or ground source heat pump, GSHP. Any which way you cut it, it comes out as the lowest cost life cycle, also the lowest bill. What it is not is the lowest upfront cost. And that is a critical piece, but that most efficient, lowest cost energy on the life cycle is fundamentally a result of efficiency. And so when you're starting out trying to solve the thermal energy system of the future, choosing the most efficient and the most cost-effective on life cycle is kind of a way to not fight physics and to give yourself some headroom to solve all the other problems. So the proposal in 2017 to use existing technologies configured in a slightly novel way to interconnect buildings with this most efficient heat pump to a distribution system that kind of is the next evolution of district energy that allows for utility growth. And then by building that distribution system, accessing this thermal energy opportunity that I just laid out, which includes the boreholes that are anywhere and everywhere from geothermal, but it also includes all of the other thermal resources. And a number of these really haven't been quantified. But there is a thermal opportunity all around the built environment. And even when we talk about the urban heat island effect, that too is a thermal opportunity. So the interesting challenge and the interesting opportunity of this thermal network infrastructure, it is entirely old tech. All of the components have been around for 50 years. It has got a really nice long life cycle. And it is kind of new, the approach to distributing it in a community, and a few small pieces about the design and approach. So there's a large, as it scales across the country, and there's now 12 states with laws implementing thermal energy networks in some form, there is an increasing confusion around terminology. So this is like the driest slide ever, I apologize. And yet it's really important because district energy has been around since the Romans or before. So what is new about this? What is new is that as district energy has evolved, it's come down in temperature to increase efficiency. Again, the efficiency is going to get us right to our next topic, which is the grid impacts. And as it has evolved all the way to ambient, suddenly it can provide cooling and heating from the same system, and the efficiency jumps up. That shifts to a decentralized, where there are heat pumps in the building, rather than a centralized plant. And so the shifting to single pipe from two pipe, which is what you will find in the newest district energy, a 5th generation two pipe in Europe, is what has happened here in the US with thermal energy networks. And having geothermal on it can make it a geothermal network. This is my best clarification of the technology naming. It does matter because what it is determines what you get. And so that shift from a district to a network in the language really is about the modular growth opportunity. This kind of interconnectability, common carrier aspect of this, pipes filled with water, like really simple technology, minimizing that cost, but opening up the thermal market. And so you can incrementally interconnect and grow. A quick case study from Colorado, the first implementation of this growth and technology that we know of began in 2007. It grew 5 times since then, has extraordinary output numbers, and working with Michaels Energy and Xcel Energy, we were able to put out a report showing that it had a efficiency on average annually of 5.7 COP or 570%, with a winter peak efficiency of 890%, which is so high it's almost feels unbelievable. I promise you, it's actually just physics. They are moving energy around, storing energy, and addressing not just their costs and even their water use, but also through scaling, bringing the cost of the infrastructure down, which is, I think, a critical piece. And finally, through that approach, they also discovered, and honestly, this was a discovery rather than intention, that the grid impacts of their growth weren't showing up. And this was the very first indication, the very first graph that anyone knows of, that this kind of system could have phenomenal grid impacts. And so they grew from 800,000 square feet to 1.2 million square feet. And Xcel actually sent them this graph with a note that had a few expletives because they were expecting load growth and had designed for load growth, and there was no load growth. And so this really, really piqued our interest, and we began digging into the interconnection between efficiency and the grid. And I think this is really important, possibly slightly too small, I apologize, but if you have different efficiencies, I have them as COP or COP, you get a different load profile when you electrify buildings. So this is on the green, where we are today in the US. Each of the other lines is where we would be if we electrified all buildings with different technologies. So the efficiency of the technology drives the impact on the grid. And what you see with the red, of course, no one's going out intending to put electric baseboards to electrify. That would be nuts. We all agree, I'm sure. And I want to point out that peak, that winter peak, would be near impossible to meet. And also point out that most heat pumps deployed on an individual building basis have an electric resistance backup, What does this mean? Unfortunately, it means that if that is how we have deployed and we hit a crazy winter peak and all of those electric resistance backups come on, we need that grid, that red line, which is a problem. And so trying to figure out how to address this efficiency, how to minimize the grid impacts of our building decarbonization. When we go to the more efficient technology, we drop that grid impact. And thinking about the utility scale, that network geothermal, we suddenly can move any backup to central and really dramatically gain the grid impacts that we need in order to get there in time. So there was an amazing study by Oak Ridge National Lab for national grid impacts of just going from air source to ground source in 2 scenarios. So there was a grid decarb and ground source heat pump and an electric future and ground source heat pump. The numbers were stunning nationally, totaling $1.5 trillion of savings on the grid alone from that move for 68% of buildings in this scenario. For Massachusetts, I have pictured at the bottom, the authors calculated that for us in Massachusetts, that electric future, which of course is our legal mandate in Massachusetts, would result simply from moving from air source to ground source in a 36% reduction in electric load. So that's a big deal. And that's why I think that this FOG really needs to think deeply about this technology. We are at HEAT thinking deeply about this. We've run an incredible research collaboration. We've built a model around the first projects, a data bank in order to learn rapidly. We're currently doing a READ study for the electric grid with NREL and are moving into doing a direct measurement of the grid, like line meters and so on, from around a project to try to move to quantify this impact because, of course, it's not on the balance sheet currently. There is no monetization of a grid impact on a thermal network currently, unless you're on a campus. And gosh, they are spreading all over campuses. So very, very rapidly, this has piqued so much interest, and I'm sorry I couldn't say more, but there's legislation spreading across the country. There are more than 26 gas utility projects alone, let alone all the other projects. Here in Massachusetts, we had a Kickstart program. We have 12 community-initiated projects, several more utility projects. And it's been so interesting as a form of sustainable development that the World Bank Group is now investing and building in 10,000 building scale deployments of exactly this technology in 7 countries. And they keep coming to visit us here in Massachusetts. And the recurring theme is energy independence and grid stabilization and peak cutting. So you're going to hear next about a project, I believe, here in Massachusetts, which I care a lot about. There's a beautiful picture. And where we are now is we have proved the potential of each of the outcomes on the right, including this extraordinary grid impacts. But we really are in the development phase where we need to bring down the costs. First to second loop is a 50% reduction so far, and need to figure out how to regulate, operationalize, and deploy and build a workforce. So all that, but the grid impacts potential is massive and the thermal opportunity is beyond scale. Good.
Right. Thank you, Zainab. That was a great overview of potential and what's going on, I think, in other parts of the country. And so right now we're going to transition a little closer to home. So we're going to have Dennis Carlberg from Boston University. Dennis is their Chief Sustainability Officer and was instrumental in getting what we all know and love as the Jenga building up and running. So Dennis is going to talk a bit about their journey and also what that building provides and a little bit more about some of the greater potential that's out there. So really appreciate, Dennis, all you've done. And I know you also are you the co-chair or the chair of the Green Ribbon Commission Higher Ed Working Group as well?
I'm co-chair of the Green Ribbon Higher Education Working Group.
Great. So I know that, and just for folks on this phone, that working group is been instrumental in really advancing discussion, policy dialogue, as well as action around use of geothermal and thermal networks, with hopefully lots more to come. But they are an incredible source of information if anybody wants to talk to the campuses that are putting a lot of this in practice.
Well, thank you, Melissa. I'm excited to have the opportunity to speak today. Appreciate the invitation. I'm joined with Tom Martin from BR Plus A, our mechanical engineers on the project. So let me just get started. Just for quick context, BU is a leading R1 private research institution with over 36,000 students. The university occupies 15.6 million square feet in 370 buildings of wide ages and types on 3 campuses in Boston. Our campus energy use intensity is 118 kBTUs per square foot per year. That's down from 150 kBTUs per square foot per year in 2006, which is the base year we use for all of our metrics. So in 2018 or 2017, our Board of Trustees approved an ambitious climate action plan, which really is driving what we're doing these days. It set 5 high-level goals. Number 1 is to prepare our campuses for the impacts from climate change that can no longer be avoided. Number 2 is to get to net zero direct emissions for the university's operations by 2040, which is really going to be a main focus of the conversation today. But to also act on indirect emissions, those emissions we compel by how we move, what we buy, and how we waste. And then integrating the climate action plan and climate change into our educational research missions and into the climate action plan itself into the university's strategic plan. So just want to talk about one example, the Dewan Family Center for Computing and Data Sciences. This building was on hold while we were working on our climate action plan. Once we had the climate action plan, the design team was asked to do a fossil fuel-free building, which is why we're here. So I want to talk about the top 5 reasons this is our most sustainable building yet, I'll stress. So just some quick stats. It's 19 stories tall, 345,000 square feet. Its measured site EUI is 40 kBTUs per square foot per year. When we include the solar associated with the project, that's 26 kBTUs per square foot per year. And this is our first fossil fuel-free carbon neutral building. So reason number 1, resilient design. The university's climate action plan established an elevation of resilience, above which all critical systems and equipment should be located. The first floor of the center is located 1.25 feet above our university's elevation of resilience. Reason number 2, and really the focus of the conversation today, is to get to net zero direct emissions for the university's operations. If we design this building to meet the very energy efficient standards of the Massachusetts Energy Code, when the building was permitted, it would still produce nearly 1.4 million kilograms of CO2 equivalent annually. Using strategies to aggressively improve building energy performance, we reduce consumption by about 30%. And Tom will talk a bit about this in a minute. Using the thermal mass of the Earth for geothermal heating and cooling, and Zainab, thank you for the explanation of this term. It's a problematic term, but that's the term we're using. But using geothermal heating and cooling, we eliminate the need for natural gas. There's no gas line connected to this building. That was especially bold in 2018 when we made that decision, but allows the building to be fossil fuel free. Switching the energy source from gas to electricity allows us to source that energy from renewables, from BU wind. That allows the building to be carbon free. Energy efficiency starts with the building envelope. Exterior louvers keep the sun's heat out in the summer, and triple glazing helps keep the heat in the winter. There are 2 curtain wall systems in the building. The first type is a diagonal louver system. It has approximately 60% vision glazing and is located at the perimeter of the deeper floor plate to drive daylight deeper toward the core and provide indoor spaces with natural light and a sense of the outdoors. The second type is a mirrored sawtooth. It is approximately 40% vision glazing and located at the perimeter of the single bay depth floor plate, where natural light does not need to penetrate beyond the depth of a single office. The next step is to reduce energy consumption from the thermal and ventilation systems. Most buildings push air through ducts to distribute heated and cooled air. Rather than air, this building relies on water to distribute that thermal energy. This means of transferring energy through water is much more efficient than air alone. The thermal ventilation systems are fully decoupled here, allowing the efficient movement of thermal energy to chilled beams using water to move that energy. Tom, do you want to add anything here?
Uh, sure. When we were designing the mechanical system for this building, um, load reductions was the priority. So using a dual wheel DOAS serving fan power boxes serving chill beams allowed us to use smaller dedicated outdoor air systems. So the fan power boxes get return air from locally to drive the chill beams. And back to you, Dennis.
Thanks, Tom. To create that healthy indoor environment, buildings require substantial amounts of fresh air from the outside and replace the stale air that's within the buildings. These air handlers are an important part of the energy recovery system of the building. These energy recovery devices have heat recovery wheels, which transfer outgoing thermal energy to the incoming air without mixing the actual air. These dedicated outdoor air systems also dehumidify the incoming outside air, thus making the distributed air more comfortable and removing water from that air, which would otherwise potentially condense on the chilled beams. Tom, do you want to add anything here?
Sure. The passive dehumidification wheel, that reduces the dew point and absolute humidity that allows us to downsize the dedicated outdoor air system. So again, the primary focus was load reduction, so we can, use the geothermal system for most of the heating and cooling. And back to you, Dennis.
Thanks, Tom. This is a good part. The primary thermal system for the building really lies underground. There are 31 geothermal boreholes drilled 1,500 feet deep to heat and cool the building. That's twice as deep as the John Hancock building is high. The heat pumps remove excess heat from the building in the summertime and store that in the ground. During the winter, we pull that heat back out of the ground to heat the building. The bore field has 31 closed-loop boreholes using water as the thermal transfer. These bores are connected to a plate and frame heat exchanger in the basement through 9 circuits. Water is used on the ground side to the plate and frame heat exchanger. A glycol water mix transfers the thermal energy from that other side of the plate and frame heat exchanger to the heat pumps to allow those heat pumps to operate during colder or at colder temperatures below 32 degrees Fahrenheit. The system is sized to provide 300 tons of cooling or 90% of the thermal needs for the building. Electric backup boilers and chillers are designed to cover that last 10%. Early in the design process, the team looked at what it would take to do 100% of the thermal load of the building with geothermal. That would have taken 100 bores to get to that 100 bores total, not 31, to get from 90% to 100%. We needed to go 1,500 feet deep into the ground to reach the thermal capacity needed in this dense urban environment. So we didn't have a lot of space to do 500 or 800 foot deep bores. We're using a concentric system rather than the typical HTPE U-bends. And just to note, the bedrock on campus is about 200 feet below the surface. So we needed to go deep really just to get to a high performance bedrock. So here's a modular heat pump located on the 18th floor. Also located on the 18th floor are the backup chillers, 2 of them, and 6 backup electric boilers. Here's the modeled load profile for the building. This is obviously a cooling dominated building. We first sourced the thermal energy with heat recovery within the building. Then we tap into the ground source for the thermal energy for the heat pumps to, again, store that excess heat in the summer and extract that heat in the winter. And then we tap the centrifugal chillers and the electric boilers and those electric boilers just pick up those few hours of the peak periods during the year. Tom, do you want to add anything here?
Sure. So this is a hybrid plant design where we have heat recovery chillers, ground source heat pumps, centrifugal chillers, and electric boilers. And I think the biggest challenge is, getting the staging right to make sure that this system operates the way we need it to. So as Dennis said, first stage is building simultaneous, so that's the dark green. The second stage is ground source and heating mode or cooling mode. And then the final stage in heating is the electric boiler, and the final stage in cooling is the centrifugal chillers. Back to you, Dennis.
Thanks, Tom. Okay, so we couldn't generate a meaningful amount of clean energy with solar on the building, less than 1%. So we added solar on other roofs on campus. These are generating over 1.1 million kilowatt hours of clean energy annually, equating to about 23% of the center's electricity needs. The building uses electricity which is matched by the BU Wind project, which is located in South Dakota. BU Wind came online in December of 2020. The project is matching 100% of the entire university's electricity needs and has reduced BU's emissions by 53%. According to the US EPA, BU's 205 million kilowatt hour power purchase agreement is the second largest single active PPA by any college or university in the EPA's Green Power Partnership. It puts BU in the top 100 along with Google, Microsoft, and Walmart, and has garnered the EPA's 2021 Green Power Leadership Award. To my knowledge, in 2018, when we signed this contract, BU was the first to use the marginal impact method, which is now under consideration for inclusion in the Greenhouse Gas Protocol. We found a project that could displace some of the dirtiest electricity generation in the country to leverage that investment in order to make the greatest impact possible on global greenhouse gas reductions. Reason number 3, indoor environmental quality. The building is designed to create a healthy, productive, pleasant place to learn and work. The spaces are interconnected with substantial access to daylight and views, providing a network of spaces where collaboration can thrive. Reason number 4, outdoor environmental quality. Green roofs step up around the building to provide access on 7 levels, reducing the urban heat island effect and providing rainwater retention. And they're spectacular. Reason number 5, reduced embodied carbon. We have reduced emissions associated with building construction by more than 6% by modifying concrete mixes and extending cure times. While 6% doesn't sound like a lot, it is a strong beginning, and only just the beginning for BU. With great leadership, talent, and focus, our project has received LEED Platinum certification with 10 points to spare. And we really need to talk about performance. So, Tom, do you want to just tell us a little bit about how the measurement and verification process is going?
Sure. So the past year or so, we've been gathering sub-metered data, electrical data, through the BAS to understand how the building's operating. So as Dennis said earlier, we're measuring about 40 EUI. Our design target was 42, so we're exceeding that, the design target. We're also gathering detailed geothermal system data, including temperatures, hourly temperatures, entering and leaving the bore field, what equipment's on, whether it's the heat recovery chillers or the electric boilers, what load they're doing. So really getting a good understanding of how the building is performing overall in the hybrid plant. And we'll use that data to apply to new projects on campus to expand the geothermal system and potentially use this asset for other nearby buildings. Next slide, Dennis. So as I said, as we went through this load profile, this was the measured. We don't yet have or this is the modeled. We don't yet have the measured data yet, but the centrifugal chillers are operating a lot less than what's shown here, maybe 5% of the year. Boilers are operating about 5% of the year as well. So generally speaking, um, uh, performing well. Anything to add here, Dennis?
I think it's important to note how our in-house team working with BR plus A and the commissioning agents really worked to um, learn from how the building is performing and optimize its performance to get to these numbers. So it's really kind of an ongoing effort. Happy to talk more about the commissioning process if you want. But I guess Tom touched on it, but we have since we're performing better than designed, there may be an opportunity in the future to really connect some of this bore field to adjacent buildings and really begin to have a thermal energy network. That's definitely something that we've got to look at in the future. So really, this gets to what's next. So for starters, we're really addressing our existing buildings. We've aggressively been addressing emissions from BU's largest emitters. These are our largest two. On the left is the Center for Biomedical Research at 700 Albany Street. We just completed a 3-year multi-million-dollar project to upgrade the mechanical systems, which we expect to reduce emissions from this building by 30 to 45%. On the right is our second largest emitter, Warren Towers. We are renovating this over the course of 3 years, one tower per year. We're taking this from BU's second largest emitter to a non-emitter. So the tough problem for our campuses is our existing buildings. And then we're updating our climate action plan, not adjusting the strategy, not adjusting the goals, but really looking at the strategies. A lot has changed since 2017 when the plan was approved. We've reduced our emissions by 66% from our 2006 baseline. And now over 93% of our emissions come from heating our buildings, 74% from the natural gas we burn, and 19% from the steam we buy. These emissions are our focus. So learning from what we and others have been doing, we're exploring thermal energy networks on our campuses to develop an update to the plan, which is looking at 25 years, even though we have a goal at 14 years. We know the work isn't going to be finished then. But even if we do all of this, we still are not meeting the scale of the climate challenge. BU and the Boston Green Ribbon Commission hope to move from this problem-solving focus from the scale of individual anchor institutions to the scale of the greater Boston area. I hope we can talk more about that soon. Melissa mentioned that a little bit earlier, and hope that we can tap a 5th-generation thermal energy network in the not-too-distant future. Thank you. And back to you, Melissa.
Great, thank you. Really appreciate that, Dennis. We do have one question for you. Question is curious as to which OEM provided your enthalpy wheel.
Tom.
So the units are ventral units. The wheel I'd have to look up, but I can get back to you.
Okay, great. When you find that, you can put it in the chat. That's great. All right, fantastic. So now we've heard about kind of how geothermal networks, or how geothermal works. We've heard about an application for a building. Now I'm going to turn it towards Nikki Bruno from Eversource, who could talk about geothermal as a full network and how we're seeing an application here in Massachusetts in Framingham and some of the lessons learned. So I'm going to turn it over to Nikki.
Hi, thank you, Melissa. And good morning, everyone. Thank you for having me. Just going to I just have some brief slides that I tried to keep to pictures because I wanted to use the time really to talk to you all about our experience in Framingham as an example here of what we think could happen in the future. Can folks see my slides or not? Is it not taken here? Okay. How about now? Is that any better?
Don't see them.
Oh, okay. I apologize. I always have trouble here on the Zoom platform. All right. I will try this.
Oh, there you go. Wait, hold on. It's coming. Perfect. There you go. You got
All right. Okay, I'll put this into presentation mode then. So good morning, Nikki Bruno, the Vice President of Thermal Solutions and Operational Services for Eversource. And my team has had really the opportunity to take on the Framingham project from inception. And I really just wanted to rebase folks with this because there's been a lot of policy and other changes that have happened since this actually was conceived. And Zainab, I love when she goes first because she sets the groundwork for what we're talking about in terms of thermal networks. And in short, we're looking at ambient networks here in this case. I don't like the word shallow either because somehow 1,000 feet under the ground doesn't seem shallow to the everyday person. But really, he'd had a lot of responsibility and credit for this narrative of working with the gas utilities and specifically Eversource, born out of leaks really on our gas system, to come up with, hey, is there another solution that really leverages a lot of the good work we do every day on the gas side at the utility, but decarbonizes the product we're giving to customers. And so what happened is, in our NSTAR rate case through the regulatory proceeding at the time, we had proposed 3 innovation projects around network geothermal, and the option that stuck was what you see here on the map. The department had directed us, according to what we had put forth, go find that neighborhood, urban, dense environment, find mixed use buildings, find, they weren't prescriptive about retrofit versus new construction, but make sure it's in your gas service territory and see what we can learn from deploying a system like that. While I really appreciate the foresight of that department around not being prescripted on how much residential to get, how much commercial load to get. There also was no rule book, right? So you're going to see through my talk at least and through others here, this is really the beginning of revamping an old technology, but there's no rule book on how to do this solidified. We are trying to objectify what we can, and we're trying to be open and flexible to take in what we learn as we go, which there have been a series of learnings on the pilot already. I think that's hard, right? For these mature, just when you think about the culture of change that we're all talking about here, how do we solve for this emissions reduction mandate in the state? How do we do it being mindful of affordability, of customer adoption, and of all the suites of technologies out there, to ask companies, agencies, groups that have been in this regular routine for so long to really innovate? That's difficult in and of itself. But I'm proud to say we tried to embody that here through Framingham, and I think we did a good job of that. What we ended up with is a square mile loop, and maybe some of you have already heard about this, but really we got every type of fuel source conversion. It feels like we didn't just convert gas customers to geothermal. We had delivered fuels, oil conversions on this loop. We had electric resistance on this loop, which I think is really important as we think about decarbonizing the peak and how this geothermal network can really affect not just the gas side of the equation, but the electric side. It's a single pipe system. You can do a dual pipe system here, but we chose single because we have always had an eye towards expandability. We like to think of this as really the, similar to the gas system if you start and then you have these modular build outs to increase efficiencies as you go, we want to be ready for that, right? So 40 buildings, roughly 140 customers, and we had all types, single family, apartment buildings, duplexes. We had small businesses connect to this loop. We had municipal buildings connect, which is really in my mind, I've said it before, but a true testament about believing in the system. And we had, must-run facilities. We have, I believe it's the oldest fire station in the city of Framingham connect to this loop. So when you think about that and the customer dynamics, what I'll talk about, or what I like to talk to folks about, is everybody is unique, right? And you're not going to please everybody per se, but we do have the job as a utility providing the level of service that they expect, right? And so geothermal to us was no different. We just felt like we had to communicate more frequently, sit and kind of handhold, if you will, with the customers, because while we in this room may know about this technology, even if we hadn't thought about it configured in our heads this way, many folks had no idea this existed, right? And so you're starting really from scratch. And we have 3 bore fields. You can see the little cones demarking where they are. Those are really, our thermal source. I like to think of them as, our thermal supply, hyper local, right below our feet, which is super exciting. And it's one type of supply, right? And we could go on about different kinds of thermal supply, but the boreholes connected to that 1 mile loop, and then service lines into the buildings connected to a ground source heat pump are really the entire system here that we were responsible for developing, executing on, installing, and now operating and maintaining. So just a few pictures. I'd like to talk versus inundate you with words. This is maybe a softer side of the discussion today, certainly, but I think it's a mission critical side. We are collecting data on the pilot, and actually a shameless plug, we're going to be doing a webinar as part of our annual stakeholder engagement later this quarter, which we'll make sure folks can attend and get the list out to you to sign up, where we'll talk a little bit more about the operating data. As you can imagine, some data sets may feel familiar to us, some are a bit new, and so we're just making sure that we have a consensus around that data. I know Zainab mentioned the Leg Up team who's been working with us hand in hand about data they're augmenting from the Mass CEC grant. So we really are appreciative of that grant and the partnership with those organizations. But when you think about data from a customer side, we probably didn't even realize we were collecting as much as we did, right? I mean, we really tried to go over and beyond for this project, understanding that perhaps for the next go rounds, it may not be necessarily a sustainable model, but just like you would think about a business development trajectory, right? When you start doing something new, the first couple of projects are going to be very intensive. You're learning, you're trying to get the word out, you're trying to market, if you will, advocate for what you're doing. And then as you do more and more, and as the familiarity with the technology, with the concept, with the working partners that you're dealing with becomes more commonplace, you can kind of lean on that goodwill you've built up, right? That trust that you've built up. And, what we found in the community, and specifically with the city of Framingham, is, probably like many folks out there, right? You get a utility bill, you work with the utility, the DPW and other facets within the city work with us quite a bit, and obviously on different levels than the average ratepayer, but there was a bit of a lack of trust, or at least kind of a neutral feeling. And so we wanted to bring that from, negative or bad, or even neutral to good, because we had laid out with both the customers and the city that we're not going to be perfect here, right? That's just an unrealistic expectation. But we want to make sure that when we run into bumps and bruises along the way, that they're quick healing, that they're quickly overcome. It's essentially kind of how I think about entrepreneurial approaches to business, where if you're going to fail it out fast, learn a lot, and move on. And so we tried early days to get into the community and do a lot of really, in my mind, really neat things. Introduce a girl to engineering, promoting STEM, using thermal experiments similar to what our thermal network was going to do in the neighborhood that abuts the school these girls were in. We had media tours and site visits from all across the globe. And then most importantly, for the customers that were actually connecting, for the city that we would be working with, getting permits with, hand in hand as things came up, we were meeting folks where they were. So really embodying that environmental justice definition as the state looks at projects and saying, hey, let's get into the community, have office hours there weekly during construction, have direct outreach lines, have our customer folks go to homes, and as long as they need, sit with the customer, make them feel comfortable with the proposal, with what we're offering, and also, with if they have any problems, who can they talk to about this? And if it's not just us, do we even have other resources that they could lean on? And I think that really worked. We actually had a lot of customers who offered to help host our little tent there you see on the right. And it's the little things, right? Because people are so busy these days, right? They're concerned about their wallet, what they're paying for, what they're getting out. And, as you all know, time is your most valuable resource. So to see the customers giving back to us, really working with us as a partnership, that was, I think, a great sign of all the good work that we had put in on our customer team. And so, we're going to be following up with some surveys, with some other outreach to customers to understand, in my mind, one of the 3 big metrics that this pilot is looking to test, which is customer satisfaction. are folks pleased with the service? And that can be a very subjective term in terms of data. And we're trying to make it as objective as possible. So things like quality of comfort within the home, within the building, things like, impact on bills. We are tracking some of that. And as everybody faced this winter, we had a more seasonably cold winter, right? So our first winter in operations really encompassed a lot of challenge with affordability narratives that were going on, for those that weren't necessarily on the network. But it's important to think about this holistically. As Zainab said, the dollars to install these projects, and now I'm moving to just show you just some of the intensive construction we had to do, are not cheap. However, I think if you can step back and think about bill impacts, if you think about the way folks are using energy, what their expectation of comfort is, as more and more folks expect air conditioning, cooling in addition to heating, from a space conditioning perspective, we think this technology and this offering holds a lot of promise. I think it's now, as we go through the construction data and the cost of conversions, we recognize that the building side retrofits are really, really hard. Each one is unique. They're very costly. So that's been a problem that the entire ecosystem has to solve. It's not just, certainly for my team to figure out on our own, but we want to contribute our learnings to that. That was the biggest cost driver. And so, we're thinking about, as we go forward, where is the low-hanging fruit, if there is such a thing? Where can we leverage our skill sets? As you can see in the middle photo here, installing pipe underground is something we do every day. Where can we do that, and also complement the efforts of, say, retrofits or building out new buildings that are ready for the transition? And so I think we see two major opportunities, where the delivered fuels folks are the ones saving right now the most money on the bill. And again, it's early days. We have to make sure we have the data clean and normalized, if you will. But there are still about 30 to 40% of homes on delivered fuels. Could this be an option for them that's more cost effective, perhaps better quality within the building, et cetera? And then also the new construction market. We see that as something that dovetails with geothermal really nicely, where you have bans or kind of restrictions on new or major renovations in certain cities and communities throughout the state. We see geothermal as an option to electrification, as an option to gas, which may no longer be available, and certainly delivered fuels that can provide those new construction developments with a very efficient space conditioning opportunity. And, there's a lot of economies of scale when you're starting fresh. We unfortunately had no new construction on this loop. So we took the hardest first, but, we often see synergies where builders or developers come in, they have an open trench because they're putting in sewer lines, other utilities. And so we can actually dovetail and put our pipe in the ground at the same time. The building retrofit is not a thing, right? They're literally building from the ground up. So you have a clean slate. So we see some opportunities for cost savings. Additionally, we are not afraid of working with multiple stakeholders, multiple, community members or customers. That's what we do every day. And I think it really delineates us and why the utility should play in this market space. However, with a developer, oftentimes it's a singular point of contact, right? So you can focus all your energy, tailor your approach with that one customer, to really make things move quickly, move efficiently, and that results, or we expect that would result in some cost savings. So we're really excited about the new construction market, and it's incumbent on us to get that vendor ecosystem going, right? When we talk about how to decarbonize the peak and the actual technical effects on the grid, before I just mention a couple things on the electric side, what I did want to share with you all is, there is a vendor ecosystem here that we need to be a workforce that we need to be prepared for. And I like to talk about drilling. There's not many drilling firms out there. The ones that are, may not even be in this region. And so, as you might imagine, that artificially or otherwise increases prices to install things like boreholes. I know HEAT and other organizations are really looking at this from any way they can. So are we. We want to make sure that we're providing the right signals to the marketplace for companies to come to do this work with us. But that is incumbent on us to kind of drive that marketplace, right? In addition to other stakeholders. So we're thinking about procurement strategies, about ways we can do that, because that's how we're going to lower costs. Getting more of these out there, understanding what the workload is, what the barriers are, whether it's regulatory, whether it's policy, qualifications, certifications that we need to work on. So efforts are underway. But that is going to be a real challenge that we need to overcome to drive the market here in the New England area and in Massachusetts. And so I guess I would just finish with saying, we've anecdotally, again, we're qualifying the data, right? But anecdotally, we've seen some interesting patterns. And I think about, as we talk about decarbonizing the peak and the build out you might need to achieve these emissions reductions, thinking about the electric side is really interesting. Geothermal truly becomes a hybrid technology. So from a gas system perspective, we do feel like we're well suited to install these systems. Feels like our bread and butter, and can help on the gas side. It also helps on the electric side. And we have a population in Framingham, a low income elderly housing authority set of customers that were basically on that electric resistance that Zeynep had mentioned earlier. Very inefficient. Oftentimes we find these installations in areas where they needed a cheaper option, unfortunately, but the operating cost of that, or the OPEX for a system like that, is not great for the customer. And so we've not only seen ways that we are able to reduce the load by bringing those folks over to geothermal, but also seeing that impact on the bill. And so we're trying to use that data anecdotally to say, how does that drive our strategy about looking at the next site, looking at the next retrofit, where perhaps it's electric resistance, and we can help both, the gas set of customers, but also the electric side. So I think there's a lot more to come. There's been a lot of interesting studies that were talked about today around, larger scale impacts and how that translates into the state of Massachusetts. I think what we're bringing, or will bring, is the actual on the ground data onto how this is affecting our electric grid discretely in the Metro West area, which will also be really good empirical information, so we can start thinking about the overall strategy to build out. With that, I apologize. I want to keep time here, but I'm happy to take any questions. It's certainly been a journey. And I do think that this is a lot harder than probably a lot of folks think. But we're up for the challenge here at the utility, and looking forward to what's next.
Great, thank you, Nikki. Super helpful. It's a great project, great example. We do have 2 questions for you, and then we had a question in the chat that Zeynep and Dennis answered, and if you want to chime in as well. So first question, Eversource Geothermal Framingham, is there a plan for a phase 2 pilot elsewhere, or an expansion of the existing pilot at this time?
Sure. So what I didn't get to is HEAT is the lead grant application, but we won federal DOE funding to do the design work of a phase 2. So roughly doubling the size of the existing pilot. That work was completed, and in December of last year, we had gotten the go-ahead that we were going to be awarded implementation phase money to actually build it. The federal administration obviously had changed over at that time, and there's been a lot of back and forth at the federal level, but we're eager and optimistic that we'll receive that money and move forward. Geothermal is certainly on Energy Secretary Wright's agenda. I think it's number 3. It's an oddly bipartisan technology, which is exciting. So more to come, I'll say that. But HEAT certainly has been a great partner with leading that grant, and we are the execution partner, ready to build.
Fantastic. Second question, how important do you think the municipal support and active outreach to residents was in getting Framingham project realized? What might be the role for municipalities in proposed gas non-pipeline alternative projects to reduce reliance on an asset like Everett? Kind of 2 parts. So 1, how important was it? And then 2, could you use this in other applications?
Sure. So the first answer is easy, very important. I think, every community, much like every customer, right, they're different. And some have different priorities, different issues they're balancing. We actually had woven in community or municipal support as part of, what I said when I was writing the rule book, or we were writing the rule book, we wrote that into our matrix on how to evaluate where to actually bring this pilot. The good news for us is it felt like a lot of the sites that we were looking at had communities that were super eager and continue to be eager and want to talk to us about these systems. But that's important because, I have heard in some instances where some communities are not as excited about this particular option, and that's okay. They may have a different plan, but to fight City Hall, I understand why that's a cliche. We know how to work with the cities and how difficult it can be from time to time when you're not aligned. So I think it's absolutely critical. We are also thinking about this for non-pipeline alternatives, how we can, leverage a system like this. I think the trick is we see like a floor for a system like this where, you need a certain type of, tonnage to make this more economical, I'll say. I know like I said, we're working on costs here. Something like Everett is a very big load to solve for. So, that's a series of these systems across multiple municipalities, as I understand it. So, that would be a multi-phase effort. But I mean, in terms of the general sense of, can this be an NPA? Yes, we do believe it can be. And, again, we're looking at what opportunities this may prove out to be for that NPA process as we're tracking that in our climate compliance dockets.
Great, thank you. Great answers, great questions. And then we have a comment and a question in the chat. This one was from Tufts University. So I'm already sold in the life cycle benefits of geothermal heat transfer. The first cost, as Zainab mentioned, is significant. Does the pending Energy Affordability Act help with this? Interested in answers from Heat, BU, and Eversource. Thank you. Zainab piped in on this one, so if anyone wants to, it's in there, but I will summarize. She did say yes. Key to unlocking thermal energy is the financing structure. The affordability bill has a whole tool shed of possibilities in it to address the need for the upfront infrastructure investment to get a system that can deliver on affordable energy, including utility financing, on-bill financing, other innovative financing, and more. Happy to talk about it, but it's key. Dennis Carlsberg, I think, gave a thumbs up to that. Nikki, anything you want to add?
Yeah, I would just say I was excited to see Geo in that bill because I do feel like, there's been a ton of focus on air source heat pumps. And the reality is, for me, we need to give customers choice. So Geo should be a choice that's available. And, the efforts to see how geothermal can play, in conjunction with campuses from the utility perspective, or, other opportunities, even to understand, how Zainab had flagged it, and I didn't even get into this, but how to monetize the benefits. That's going to make a huge difference on how people see the value, because as we know from customers doing a lot of hard work, they money is their driver. It really is. A lot of folks have other priorities that could be equally as important, but for many, many folks, what they can save, especially in this day and age, is really important. And so if we can show fiscal benefits that these systems provide and quantify that, that's going to be important. So, and I see hints of all of that in the affordability bill there. So I'm, encouraged by having geothermal in the bill and in the discussion.
Excellent, thank you. All right, so we're going to now transition over to Vicinity Energy, and so we talked about, the first question was, what is thermal technology, what's thermal energy, and we provided an answer to that in the chat. And so we're going to be talking about a sort of another form of another thermal energy technology now. Vicinity is really leading in this nationally, globally. They're pioneering an e-steam technology, which we'll hear about, leveraging the thermal capacity from the Charles River, which is really, again, innovative, interesting, promising. So really, Kevin, looking forward to hearing everything that you're doing.
Absolutely. And thanks for having us, Melissa. I really appreciate it. And apologies on being a couple minutes late. I promise our strength is decarbonizing cities, and e-steam, it's not IT. All right. So with that, Jeannie, next slide, please. Okay. So who I am, I'm Kevin Haggerty. I'm the president and CEO of Vicinity Energy. For those who don't know us, We are the largest owner and operator of district energy systems in the States. So we own and operate 19 different district energy systems across 12 cities. And we own and operate the whole gamut. So we own and operate steam systems, chill water systems, low temperature water systems, high temperature water systems. And we're pretty simple. We just call them all district energy. But we operate the broadest and largest portfolio of these district energy systems in the States. Ultimately, we serve about 250 million square feet of building space. So the Prudential Tower, as a point of comparison, is about 1 million square feet. So we serve the equivalent of about 250 Prudential Towers. We generate about 400 megawatts equivalent of electricity. And we are currently mitigating around 588,000 tons of carbon with our district energy efforts, a lot of that being e-steam, some of it cogeneration, some of it with unique products, which I'm not going to talk about today, are decarbonized biogenic fuels. But ultimately, I think we are well underway towards decarbonizing many of the cities that we do business in, with Boston and Cambridge leading. All right, so I'm not going to talk about the rest of our systems and other electrification projects. I'm just going to talk about Boston and Cambridge today. So Boston and Cambridge is our second largest area of business. We serve about 187 customers, 260 buildings. We serve 71 million square feet. Again, so that's about 71 Prudential Towers. We serve predominantly life science universities, hospitals, commercial real estate. I think the punchline that I usually say is that if you look at the Boston skyline from any angle, our district energy system will serve about 4 out of the 5 buildings on that skyline. That's pretty typical in the cities that we do business in. We serve about 4 out of the 5 buildings on the skyline. Underneath the city streets of Boston and Cambridge, we have 29 miles of steam piping that serves many of these buildings. And I'm excited to talk about today our latest product that we are putting in place. We call eSteam. And I think we call it eSteam because we are an organization of predominantly engineers, not marketing. So eSteam is just short for electrically generated steam. And I'll talk through how we do that, but it's a really exciting product that is putting us well underway to being able to decarbonize Cambridge and Boston. Next slide. Okay. So before I talk about our transition to eSteam, just a little bit of history on district energy. As Zainab said, district energy has been around for a very, very long time. And many of these systems, including the Boston and Cambridge system, actually started as coal back in the early 1900s. Now, we don't burn coal anymore, thankfully. But coal was what the initial fuel was. In the 1950s, the systems migrated, Boston and Cambridge migrated over to using oil as a predominant fuel for heating. In the 1990s, after the oil embargoes in the 1970s, many district energy systems, including Boston and Cambridge, moved over to natural gas. In the 2000s, with the deregulation of the electric grids, New England ISO being one of them, many of these systems, including Boston and Cambridge, moved over towards cogeneration. And now we're facing the next inflection point. So this is a normal transition. Moving the fuel source of how the district energy system makes its energy is very, very typical for district energy business. It's something that we undertake every several decades. So what I'm going to be talking about in the next couple slides is nothing new. Us moving away from natural gas and moving towards using decarbonized electricity as our fuel source for our district energy system is nothing new. We were very experienced in replacing boilers or pieces of equipment. And oftentimes you'll hear me say that us putting in another large piece of equipment, that's a Monday for us. That's normal. So, and also, before I talk about it in depth, these aren't pilot projects. This is actually, this is city decarbonization in motion. So these are projects that are already built or projects that are well underway and in the process of being built. Okay, next slide. All right, so what is eSteam? So eSteam is effectively taking decarbonized electricity off of the grid. For New England, it's wind and solar. Moving that electricity through existing infrastructure that we have at the plant, and then putting that electricity into 3 different types of technology, which I'll talk about here in a little bit, that very efficiently convert that electricity over to steam. We then concentrate that steam, raise it up in pressure, and pump it underground in the 29 miles of piping that we have in Boston and Cambridge, and that's what we use to heat the buildings. So it's a way for us to carbon-free or it's a very efficient carbon-free way and very affordable carbon-free way for us to be able to decarbonize the heating systems in the cities that we do business. And this is one of the areas that we strive for at Vicinity is the product that we push out, I call affordable sustainability. We've got an active customer base. We need to be able to stay within the affordable bounds of what our customer base can tolerate. And I'm glad to say that eSteam so far is a very, very successful product. Last year, we generated around 1,300 M-pounds of eSteam. This year, we generated around 20,000 M-pounds of eSteam, and next year, we're scheduled to generate around 200,000 M-pounds of eSteam. So as a point of comparison, that would serve approximately 5 to 10 million square feet. So we are going to be generating enough eSteam next year for approximately 5 to 10 Prudential towers. So we are well underway with getting this product rolled out, and I'm happy to say that it seems to be working really, really well. The other point that I want to make before I talk about the technologies is we leverage existing infrastructure. And this is a very important point. Much of the infrastructure, if you look around, it took multiple decades and billions of dollars to get in place. So for us, it's very important that when we look at solutions that decarbonize cities, and in order to provide an affordable sustainability product, we want to make sure that we're trying to leverage as best as possible, not always, but as best as possible, leverage the existing infrastructure. And we carry that note all the way through on whether it's the electricity that we're importing into the plant, whether it's the water that we're using from the Charles River, or whether it's the distribution network that we're using to get the energy out to the buildings. We're making the best use and leveraging and optimizing the existing infrastructure. The electricity that comes into our plant, these plants were built back in between the 1950s and the 2000s to generate electricity and cogeneration. So they are built around large electrical substations. Also, many of these plants were built by Boston Electric and co-located with their electrical infrastructure. So we sit on large amounts of electrical infrastructure with interconnects, and we have the ability to export large volumes of electricity, but we can also use that existing infrastructure to turn that electricity around and import large volumes of infrastructure. So we're reusing the existing infrastructure. At Kendall Station, where we're going to be deploying our heat pump, we have large cooling ducts that were formerly used for cooling some of this electrical generating equipment. We're leveraging those cooling ducts to draw Charles River water in to feed our heat pump. And then also, I already mentioned, we're reusing the existing steam distribution system so we can leverage that infrastructure. But a real theme of us being able to keep this in order for us to move at the pace we're moving at and keep it affordable is to leverage existing infrastructure. Okay, next slide. All right, so a little bit about the 3 technologies that we've deployed or are actively deploying in our systems. So the first one is an electric boiler. So we have an electric boiler, a 42 megawatt electric boiler that we started construction in 2022. It has been online since November of 2024. And this is our peaking technology. This leverages readily available technology. We don't often see large electric boilers in North America. That's because we're sitting on a low-cost natural gas island. But as you get outside of the United States, you can get off of North America and you get around the world, you'll start to see these large electric boilers in Europe. You'll see some in China. You'll see them in South America. In areas where electrical costs are lower, you'll start to see these large-scale electric boilers. So we're simply just using or leveraging existing technology that you'll find around the world and bringing it over to the United States. Our 42 megawatt electric boilers are peaking technology. Much like the electric grid, you need a diversity of sources as to how you generate. The district energy system is no different. We have to have a diversity of sources of how we generate with different operating characteristics to ensure that the steam or the energy, the heat to the buildings always stays on. Our heat is used for a lot of critical care facilities. And if the heat turns off, some of the hospitals that we serve will have to delay surgeries. Buildings would have to evacuate in some areas. So it's absolutely important that the heat stays on. We run with 99.999% reliabilities. So we have to make sure that we have multiple means of generating that energy so it stays reliable. The other interesting thing about our electric boiler is that it can turn on quickly. So it can respond within a couple minutes. And one of the interesting things we've seen with this piece of equipment being available is the New England ISO grid has a large amount of solar now. So New England ISO has about 6 to 8 gigawatts of solar on, I think, about a 26 gigawatt grid. So it's a significant percentage. And it's a little difficult for the grid to predict as to how much solar may come on some days. You'll see this when we have snowfall and they have trouble predicting as to how much exposure the solar panels are going to have. Sometimes cloud cover causes this. And if there's issues with predictability of the solar, what we do run into are solar surplus events. So the solar will pour onto the grid. It'll put too much electricity on the grid. We'll see power prices go negative. We now have the ability to respond to that. 15% of the operating hours of our new 42 megawatt electric boiler were actually done during solar surplus events this last year. So we were paid for the privilege of taking excess solar power, converting that into renewable eSteam and selling it off the buildings. So it's a very, very interesting thing that we knew we were going to see a little bit of before we put this equipment in place, but we're starting to see a substantial amount of operating hours where we can use this piece of equipment to help balance the grid and balance the solar that comes on. The second piece of technology that we're going to be deploying, we are actively building this right now, is a 35 megawatt heat pump complex. So this is a high temperature, high pressure heat pump that leverages the Charles River. This turns the Charles River into a renewable energy resource. Again, we are leveraging our existing infrastructure. It allows us to very efficiently generate steam from renewable electricity. This heat pump complex will use less than half the electricity of the electric boiler in producing the same volume of steam. So this is a big part of what makes us electrifying the district energy system affordable. And this heat pump complex is already underway. I'll show some pictures here in a bit. But this will be the first of 3 heat pump complexes in this facility. And then at the end of the presentation, I'll talk about some of the other heat pumps we're looking to deploy around Boston and Cambridge. The last technology that we're putting in place is thermal storage. And just like the first two, where we do things at city scale, our thermal storage system is going to be rather large. We're looking at 600 megawatts to 1,000 megawatts of thermal storage capability. One of the great things about thermal storage is it's not particularly complex. It also doesn't take up a very large footprint. So on our existing Kendall Station plant right in downtown Cambridge, we can actually install up to 1,000 megawatt hours of thermal storage. Oftentimes you don't see thermal storage because the end product many of us need for energy is electricity. But if the end product you need is heat, you can deploy thermal storage technologies that I said are relatively low cost, not expensive, and don't take a very large footprint. All right, next slide. All right, so a little bit about our electric boiler. So this is a project that we started in 2022. This is our first step into electrification of the Boston and Cambridge district energy systems. For the demolition, as you can see there in the picture, we brought in Mayor Wu. She did a fantastic job. So if you have any demolition projects, I highly recommend the mayor. She does a great job. It took us about 2 years from concept and demolition and construction all the way to getting the unit online. So I'm very happy to say November 2024, we turned the electric boiler on. It's been an absolute success. We've been able to import electricity at costs much lower than we had originally anticipated. And we've been able to use the electric boiler, like I already talked about, to help balance the grid with these solar surplus events. And as I already said, this will be our peaking technology. So this is the technology that turns on if we have an issue with one of our heat pumps. This is the technology that'll turn on in the dead of the winter time to help augment our baseload tech. And we'll use it to continue to valley surf with these renewable surplus events on the grid. Okay, next slide. All right, and this is the one that I'm most excited about. This is our heat pump complex. So we've already started demolition on the heat pump complex. I really like the irony that we are taking out natural gas generating equipment to make room for e-steam generating equipment. And that's what this picture shows here. So this is our turbine hall at Kendall Station. We used to have 3 steam turbines that used natural gas to generate electricity. And we've removed 2 of those steam turbines to make room for our heat pump. What's actually going to be going in this space is our steam compression system, where it'll take steam that's generated off the heat pump and compress it up to full pressure so we can send it out across Boston and Cambridge. The other area that we're going to be taking over in the plant to make room for the heat pump, very glad to say, is a old coal boiler that's been retired in place. We haven't used it in decades. And we are going to be taking that coal boiler out, and it is, I'm not sure it's a coincidence or if it's just fate, but the exact same size as the coal boiler is what the heat pump is. So we're taking that boiler out, putting the heat pump in there, and we have enough room for 3 other heat pumps that we're going to be putting in this facility. These heat pumps are, like I said, exceptionally efficient. This is technology that we're not serial number 1. This is technology that is actively deployed over in Europe. I would like to say that we could take full credit for this concept, but this is something that's has been done in Europe for the last several decades. In fact, Stockholm has been using heat pumps to supply energy into their district energy systems, I think since the 1980s. So again, we're just taking technology that was deployed over in Europe, we're adapting it to the U.S. market, and we're deploying it here in Boston and Cambridge. Okay, next slide. What's coming next? All right, next slide, Gene. All right, so I talked a little bit about our heat pump technology that we're putting in place over in Cambridge. The Charles River is a great energy source. Water contains a tremendous amount of energy. There's a reason why our district energy systems, a lot of them are set up with water or steam. It's because you can put a tremendous amount of energy into water and you can use that water to distribute that energy out to the buildings. Well, the inverse is true as well. The water holds an inherent amount of energy that you can then take into a plant, pull that energy out of the water, return that water back to the harbor, return that water back to the Charles River, and use the heat pump technology to concentrate that energy and send it out to the buildings. So we're going to deploy as many heat pumps as we can on the Charles River, upwards of 3 at Kendall Station, but we're actively looking to deploy a seawater heat pump. So we have space in some areas around the harbor in Boston that we're looking to deploy this. And this is the same kind of technology that we're using on the Charles River, although it's a little bit more efficient and it is going to be larger. So our Charles River heat pump complex will have the capacity to circulate approximately 3 Olympic-sized pools of water every hour. This heat pump complex will circulate approximately 10 Olympic-sized pools of water every hour. So we have the ability to pull in a tremendous amount of water, extract that energy out of the water, use the heat pump to concentrate that energy and send it out to the buildings. So where we are with this project, we've got an e-boiler in place. We're actively building a Charles River 35 megawatt heat pump, and we are now trying to secure space somewhere along the harbor where we can deploy one of these large seawater heat pumps. We anticipate that by 2035, 50% of our district energy system is going to be using e-steam. So we'll have decarbonized Boston and Cambridge about 50% by 2035. And we are well on our way to be able to fully decarbonize the Boston and Cambridge systems by 2050. Something we're super excited about. It's a product that seems to be selling very well. A lot of our customers are very excited about. And I cannot wait until we can start continuing to build the heat pumps out in Kendall Station and ultimately get one of these large seawater heat pumps to serve Boston and Cambridge. It's a really, really exciting time in district energy, and I can't wait for it. All right.
So thank you, Kevin. That was fantastic. We have 2 questions. They're very similar. Both, love the project. Question is, what are the effects on the river? Is there a thermal impact to the river's ecosystem? Are there any environmental concerns, wildlife concerns with using the river as part of this facility and the heat exchange?
So one of the things we've been very particular about all the way through this project is being a good neighbor. And that extends to how we function in the cities with our customers, but also how we treat the river. So as part of our design, we were very particular about the delta temperature, or the temperature and drop that we insist upon with the river. And so we try to keep that as small as possible. So the temperature drop that we will put onto the river during the wintertime is approximately 4 degrees Fahrenheit. That helps us with the freezing conditions on the river, but also that helps on minimizing the effect that the temperature drop has on any kind of life in the river. And just as a point of comparison, the natural temperature stratification of the Charles River Basin, where we're going to be pulling the river out, if you go from the top of the Charles River down to the bottom of the Charles River, that's anywhere between 10 to 12 degrees Fahrenheit. Whereas we are going to be dropping the temperature about 4 degrees Fahrenheit for the small slipstream of water that we're taking out of the river. So any kind of fish or anything that's in the river, it can get exposed to the same kind of delta temperature just by simply swimming from the top of the river down to the bottom of the river as the delta temperature that we're going to be putting on our little part of the river. So that's an important part of minimizing the impact. We've done multiple studies. We've been working with the regulatory agencies on this, and everybody has unanimously come back that it doesn't have any kind of material effect on the river, and largely because of how we've been particular about our design.
Great. And then just anything else on any other kind of river life mitigation in terms of water intake, outflow, like anything like that? Yeah.
Yes, absolutely. So the other mitigant that we have is we keep the entrainment velocity very low. So our entrainment velocity is below 0.5 foot per second. So that ensures that anything that doesn't want to get drawn in doesn't get drawn in. We also have a pre-screen and a fine screen that helps ensure that we don't draw anything to the plant. We don't want it in the plant any more than it doesn't want to be in the plant. So we pull in water very, very slow, and we have several screening systems to ensure that we don't pull things to the plant that we don't want in the facility. So the slow entrainment velocity, the multiple screenings, and the very small delta temperature has really minimized any kind of impact. And the studies that have come back, the impact that we have seen on the river is really just academic. It's absolutely minor, which is one of the reasons why we've been able to secure permits for this project.
Right. Thank you. So I think we're at the end. I don't have any more questions. Thank you. So I just want to say thank you, all of our participants. Incredibly informative, incredibly helpful. incredibly exciting. I think, for all of us just to hear, what's available and what's available to us as Massachusetts as a resource. It's, it's our river, our harbor, it's the ground beneath our feet. So, this is energy that we can leverage, and these are technologies that we're innovating and expanding, right, and bringing forward here. So a lot to be excited about. So again, thank you all for your work, your efforts, and for participating today. And thanks everybody for joining us for this webinar. We said the presentations will be put on the OET website, as well as a download of this recording. And so you welcome to share with others. So again, thank you all for joining today, and thanks to our participants.
Thanks.
Thank you,
Appreciate it.
Melissa. Thank you, everyone.